Let's say that I have a key and I'm interested in what will be the environmental impact, means how much the carbon dioxide will be produced in making this key. So at first you will say that is an easy, since this key is made of steel, so the amount of steel is responsible for the carbon dioxide emission. But actually this is not the case. To make this key I need steel, and to make this steel I need water, and to make water I need electricity, and to produce electricity I need coal and other minerals, and this process goes on and on and on. So how to capture the total environmental impact of all the things, because everything that came in between, water, coal, mineral resources, have their different environmental impacts. So to find the total environmental impact, we need to develop a model, and we will be discussing in our presentation. Hope you will have a nice time learning.
Hello everyone, and I feel so excited because today we are going to learn the multi-regional input and output model. It's also called as the MRIO model. So it is a very powerful tool that you will be studying now. Let's say that you try to throw a party at your place and you just try to make a cake, the pizza and soup, and there's a couple of things that you just decided to make. So this is how a recipe looks like, that you make cake, pizza and soup, and these will be the ingredients: eggs, sugar and yeast, and the proportion that you need to make this. So this is what a recipe looks like. Now let's say you want to know what is the recipe, that if you want to make a lot of things, definitely the recipe will go much larger. And this is the case with the national economy, is that for a country you have to make a lot of products, so its recipe will look like, yes, and this is the input and output table. So what is this basically telling us? It's actually a recipe that if an economy manufactures agriculture, energy, manufacturing, construction, and the 8 sectors are given over here. So they tells you that if these 8 sectors are manufactured, then they will be requiring these inputs and in these proportions. These numbers are basically telling you about the how much amount, let's say how much amount of input is necessary, and these values are in hundreds of billions of dollars, or it can be in hundreds of millions of dollars. So these are just the 8 sectors given over here, but in reality there can be hundreds and thousands of sectors. For example, it's usual that an economy manufactures yogurt, and it manufactures electricity, it manufactures agriculture, and there are so many things that you can imagine of. So this table is for United Kingdom, must be much bigger and very big in fact. But to just give you an idea that what this input and output table is, the input and output table, it is basically a matrix. We can just draw it over here, and you know that this matrix will be having the column values like sector 1, sector 2, sector 3, and it can be to the hundreds and thousands of sectors. We can say SN, and you know whatever is on the column side is also on the row side. So this thing I'm just going to replicate it over here. So this will be S1, S2, S3, and it will all go till Sn. And so the important thing to note is that this input and output table will always be a square matrix, and we generally call this thing, we'll be talking that later. And these values will inside this matrix, the values will be in dollars, means all this value like x1, this x2, x11, x12, and you know these value will be in dollars, hundreds of billion dollars and so on. And this thing means this column values like S1, S2 and S3. These are the inputs. I'm writing it here, and these things are the outputs. So it will be just, this is how the matrix looks like. Now let's move forward. Perhaps we can understand. Let's consider a two-sector economy, a very small economy in which just only two things are produced. So this is the two-sector economy, which has sector 1 and sector 2. So let's, for our easy in our understanding, let's say sector 1 is agriculture and the sector 2 is energy. So what we have written here, we also have to write here, since it is a square matrix. Yes, energy. So you know, this thing X is actually telling you the output. This thing tells us the output, and this Y tells us the final demand, means how much the final demand goes to the final consumer. And X, again, this is the output. This X is just going to tell you the output. So and this V, yes, this is telling you the value added. So are you ready? So I'm just going to tell you that how to read this input-output table. And remember that this input and output table is for two sectors only. And in reality, there can be hundreds and thousands of sectors. But just to simplify our analysis, we are just considering the two sectors that are agriculture and energy. So how we are just going to read this? For example, you can see we want to know that if an economy wants to manufacture $1,000 billion of agriculture, then it will be needing $150 billion of input from agriculture sector and $200 billion of input from the energy sector. Likewise, if this small economy wants to have an output, means want to produce $2,000 billion of energy, then it will need input of $500 billion from agriculture. Like if you want to produce electricity from ethanol, then ethanol comes from the crop, which is the corns, that is agriculture. So you need $500 billion of input from agriculture to produce energy, and so on. And $350 billion is the demand of the final consumer of agriculture, and $1,700 billion of the demand is by the final consumer of energy. And you can see this is the final total output. The total output of agriculture is 1,000, and the total final output of the energy is $2,000 billion. And you can also see that these values is the same as these values over here. That is because the input-output table has a balance equation that input is always equal to the output. Okay, great. So now you have understood that how to read an input and output table, and I think it's time that you should congratulate yourself. Great. So now let's simplify this thing even further. Instead of saying that I want to know that what will be the ingredient is $1,000 billion of agriculture is produced, or I want to know what the ingredients will be if $2,000 billion of energy is produced. Let's say I want to simplify it, and I want to know that how much ingredients from each of these sectors will be needed if I want to produce $1 billion of agriculture, that is sector 1, and I need to produce $1 billion of the sector 2, that is energy. So instead of knowing $1,000 and $2,000 over here, we, let's say, just are interested in knowing what will be when only one is over here, and one is over here. So we are just interested in knowing when there is a unit output from each sector, then what will be the input from the corresponding sectors which are in the rows. Great. So this will be, this is the matrix, which is the answer for this. A. How did we form this matrix? How did we form? This is the question, and it's not that difficult. It's pretty easy. How do we do to find one? We know that to produce, as you can see that over here, we know that to produce $1,000 billion for agriculture, we need input of $150 billion from agriculture. So we'll simply divide this value by this thing. So if we divide 150 by 1000, we are just going to get 0.15, and this is what this is, A. Likewise, if we want to know if we are making a unit of agriculture as output, so what energy input will be? So we'll divide this 200 by 1000. So if we divide 200 by 1000, the answer is going to be 0.2, and this is over here. Likewise, if I want to know that if I'm producing this 1 unit of energy, then what input will be required from agriculture and energy? We'll do the same. We'll divide this 500 by 2000 and we'll get 0.25, that is over here. And for again, this 0.05 comes because we divided 500 by 2000 over here. So 500 divided by 2000, it gives you this. So basically, this A matrix you can see over here is telling you when the, yes, I think this is a very good representation, that this was the input and output table. It was just telling you that if this is the X, so this is what the inputs you will be needing. And this A is a simplified version of this big input and output table. It's just basically telling you that if you are producing 1 unit of agriculture, that was our sector 1, and you're producing 1 unit of energy, then what will be the input you will be needing? So it's just telling you the proportion. This particular thing is just telling you the proportion. Like if you're producing 1 unit of agriculture, you will be needing $0.15 billion of agriculture and $0.2 billion of energy. And if you're making $1 billion of energy, you will be needing $0.25 billion of agriculture. So we have just simplified this in this way. And in the next slides, we'll be using this A matrix to do our calculations. Great. Move forward. And it is clear to us that this A matrix is what we just talked about, and this Y, we know that this is the final demand of the consumer, and this X is, we know, the total output. And this A was the matrix, what we call recipe, that was just telling you in proportion, right? That was just telling you in proportion values, that if you want to produce 1 unit of one particular sector, then what will be the proportion and the ratios. So it was just telling you that proportion thing. So if we multiply the output with the proportion, the answer will be the final demand of the consumer. That's almost very intuitive to know. Yeah, so and if we shift this X towards this side, the inverse sign will come over here. So now we can see just this over here. Let me rub this, so just to make you clear. Yep, this X is the output, this X is the output over here. And just to get to know what the total output is, you just need to multiply this matrix with the final demand, and you will know what the output of this is, of an economy is. So for example, you want to know what the output of energy is of a particular economy. So you just need to put the value of the final demand over here and multiply by this. It will be telling you what the inputs you're required from each of the sectors. Now let's move on. That particular metric that we just discussed was this thing, right? That is I plus I is the, by the way, identity matrix minus 1 and y over here. So this particular thing, this matrix is called the Leontief inverse matrix, which is 1 plus a raised to the power minus 1. So this matrix is of a great significance, and it's called Leontief inverse because the scientist who developed this thing, his name was Leontief, and he even won the Nobel Peace Prize for this. So if you're good in algebra, you must know that if you just try to expand this inverse matrix, then it will come in this form, right? And the thing of interest is that when it comes in this form, this thing will be telling you the direct purchases. Yes, now what are the direct and indirect purchases? Let me give you an example. Let's say you want to make energy, and to make you want to make energy, and to make energy you will be needing input like coal. So you will be needing to make energy, you will be needing coal. So that is a direct input, that is a direct purchase. So what is, if this is direct purchase, then what is the indirect purchase? And indirect purchase is you are trying to make energy and you need coal, that is direct purchase. But to make the coal you need another kind of machineries like tractors and bulldozers and other kind of the metals. So that is the third degree kind of the input, and that is called the indirect purchases. I hope this is clear by now, that the first degree direct purchase is the one which are directly responsible to make that product, and the indirect purchases are the material that are needed to make those material that you are purchasing to make that particular input. So, and this thing, you know, it can goes on. For example, to make energy you need coal, to make coal you need extraction tools, you need machineries, to make machineries you need let's say you need agriculture, for agriculture you need to get electricity, and to get electricity you need this and this. It is a never-ending process, and it keeps going on and on and on, because everything, if you need to produce one particular thing, everything of something must be required from every sector. So this is a very powerful tool because it captures every degree of the supply chain. The direct purchases over here, and these are the indirect purchases. This is the second degree, this is the third degree, and fourth degree, fifth degree. It keeps on going on and on and on. So this is the coolest thing of the MRIO model, that it captures the direct and indirect purchases associated with producing one particular thing in an economy. Great, so I hope that you just got what this means, and let's move forward and try to do an example that how really it. And this is the total requirement matrix that we just talked about, and this is the input and output models. So they are completely linear. This means that we assume that if we want to produce 1 unit of one particular sector, then it will be having a unit output linearly. But this is not exactly the case, because if we are trying to produce more of one sector, or if we, let's say, if we produce more of the energy, then the price will go down, and that is because the economies of scales we get, and the general, there will be more discounts or something like that. So in reality it's not linear, but we are just trying to make it linear for our assumptions so that to apply our model. So input output models are non-linear. Okay, the second thing is that it considered the manufacturing impact only. This means that for example, I am making a car. So to make a car, it just considers the impact, that is all the materials you will be needing to make the car. You will be needing windscreen, you will be needing tires, you will be needing so many things to make a car. So it will be just telling you that, but it will not tell you the materials you will be needing after the car has been manufactured. Like after the car is manufactured, you will be needing fuel of the car. You will be needing, after the car is manufactured, you will be needing you know, a kind of the decoration material for the car the user will be using. So it does not tell you the entire life cycle of the entire life cycles of the car. So it will be just telling you the what happens from cradle to the gate. It does not tell you from gate to the grave. The third point is it does the domestic production only. Yes. So this is the input output model. The input and output model is for one economy only, and every country, every economy, every nation has their input and output models. Now let's say, give you an example, let's say Somalia is a country, and Somalia must have an input and output table. So let's say in Somalia they are trying to manufacture a car. So if they try to make an input and output table, it will be they need this to produce car, they need this much energy, they need this much agriculture, and all whatever they need will be needing will be just from Somalia only. I mean, they won't be needing agriculture from other countries, they won't be needing energy from other countries. Means whatever they will be needing, and whatever the input will be only from Somalia. So I'm just giving Somalia as an example, right? So this is one of the problem for the input output table, that it considers the domestic production only. Yeah, but in reality, if you want to make a car, you need the parts from Japan, you need the parts from Germany, you need the part from many parts of the world. And in fact, today the global trade has become so much that everything is so much interconnected with each other. So this is the reason that the multi-regional input-output model has been developed, that takes account the multiple region into account by aggregating these input and output models. And the third thing is that the circularity is incorporated in the model. Circularity means that you must be wondering that why is that so, that agriculture is needed to produce agriculture and energy is needed to make energy. This is called the circularity, that to make steel you will be needing some steel, to make one particular product you will be needing the same kind of a product. So this is what the circularity is. And let's move to an example, and here is just what we did before, this is an example. We'll just try to solve this one. So as you can see that this was the means this was a recipe of this particular two-sector economy that we got. So the question is, find the total requirements of $100 billion final demand of each sector. So we need to find what the final demand is. The final demand was basically Y, right? This was Y we need to find, and it is given the total requirement. Okay, the final demand is $100 billion of the each sector. So we need to find the the total requirements, means what will be the total output of each sector is necessary to satisfy these final demands. So how do we do this? Easy. First we'll convert this matrix, this particular, into this one, which is the Leontief inverse, and here we get this. It's not that difficult, it's super easy, and I'm sure you are just coming up with me. And the next step will be this is the next step. Use this formula of the Leontief inverse, this formula that we just talked about, where X is the output we are interested in. So let's say we want to know that this was the sector 1, this was the sector 2, sector 1, sector 2. Let's say we want to know if there is $100 billion demand from sector 1. This is Y1, this is Y2. So let's say this is X1, I'm labeling this, and this is X2. So this is the output that we need of each sector, and this A is particularly this thing over here, and Y1 this. So we are considering for each one. In this case, Y1 is a vector which will be 100 for sector 1 and 0 for sector 2, and in this case Y2 will be a vector of 0 from sector 1 and 100 from sector 2, because we are just interested in the output of the sector 2, what it will be. So this is what how it will be, and it is saying that, so to read this particular matrix is just telling, we are reading X2. X2 is saying that if there is a demand of $100 billion, to satisfy the demand of $100 billion of sector 2, you need $33 billion of input from sector 1, which can be seen over here, and you need $112.2 billion of input from sector 2 to make a demand of sector to satisfy the demand of $100 billion of sector 2. So I think this is a very cool and a very awesome formula. By just having this recipe matrix over here and just knowing the final demand, you can actually able to calculate what the total requirement is needed. So this is a very good and a very exciting thing to know about this. So this is why I'm just calling it is a very powerful tool. And talk about another very cool thing which is generated from this thing. That is, I can know the impact of manufacturing one particular thing, which is, we'll be talking about the impact matrix. So I can know that how much carbon dioxide is produced if this much amount of the sector in sector 1 the manufacturing has taken place, and I can know how much amount of the sulfur dioxide, carbon dioxide, ammonia and many gases I know can be emitted if that particular manufacturing is done. So this is a very good thing in that regard. So we'll be doing an example of it to make our knowledge more concrete on this. And E over here is the vector which is called the environmental burden. So it will be telling you that what will be the total carbon dioxide emissions and sulfur dioxide emission due to that particular economic activities. And R is the matrix, will be a diagonal matrix that will be telling you the impact, like it will be telling you like 250 grams of carbon dioxide is emitted if $1 billion of the output is output of sector 1, and like say 500 billion cubic sulfur dioxide is produced if let's say economic activity of $1 billion is done of sector 3. So this is just telling you the impact of each sector. This R we'll be discussing in the next slide. So it's basically telling the impact per dollar of output for each sector for a particular energy or environment burden, and you can sum up all this to get the total environmental impact. Hello. So this is an example for the impact matrix, and let's say that we need to find what the total emissions of sulfur dioxide is going to be, and the data that is given to us is that for every $1 billion of sector 1 causes 50 grams of sulfur dioxide emissions, and every $1 billion of sector 2 causes 5 grams of sulfur dioxide emission. So this data that is given to us over here is actually this R matrix. You can see that for sector 1 over here, this is sector 1 and this is sector 2, like this is sector 1, this is sector 2. So it says that for sector 1, and its R is always a diagonal matrix. So you can see the 50 is over here, 5 is over here, and this R, it just measures the impact. Since it is measuring the impact of the sulfur dioxide, so this is the R matrix. And you can see we'll be just using this formula, that is E minus, this formula. So we just have to simply plug in the values. So if we just try to simply plug in the values, R we know is this will come from here, and we know this I minus 1 is just going to come from here, and Y we know it is the final demand, which is this one. So let's just try to solve this. So if we solve this, we want to find, let's say, the impact of what if this much is produced by sector 1, means $100 billion of the demand is the demand of sector 1. So we want to find what the sulfur dioxide emission will be of this two sector economy that we are talking about. So that will be E1, means that is impact by sector 1. So let me write this in blue to make it clear. That is E1. R matrix will just simply write as it is. That is 50, 0, 0, 5, and 1 minus A minus raised to the power minus 1. The Leontief present matrix. We'll be writing it over here. 3.264, 0.33, and 1.112. We just got it from there. Great. Now we just need to put the Y value, that we need to know what the impact will be if there is a $100 billion demand from sector 1. So we'll be considering demand from sector 2 to 0 to find what the impact will be just from the demand of the sector 1. So if we do so, we'll get a vector. It will be in this way. So I'm leaving the calculation to you. It will be having some values like Z1, Z2. You can do the calculation. So these this will be just this will be telling you the sulfur dioxide emission in grams. That will be due to the sector 1, and Z2 will be telling you the sulfur dioxide emissions in gram due to sector 2. So this is the coolest thing, that it not only tells you the emission that is associated by the total emission, but it also tells you the emissions that will be due to each of the individual sector, because in an economy each and everything are very connected. That for example, if you need to make products from sector 1, you will be needing input from sector 2. So that's why it captures the impact by all sectors. So it will be telling, this thing will be telling you the impact of the sector 1 on sulfur dioxide, and this Z2 will be telling you the sulfur dioxide impact, that is the emission that will be in grams. So great. I hope that you find it very informative, and congratulations that you got to know what input and output model is and what the impact matrix is. So you should once again congratulate yourself, and please let me know if you think that I need to add some more thing to make it more clear, and your feedback will be appreciated. Thank you.